Professor Youssuf Azouzi, who is visiting from the University of Carthage as a guest to CoE-MaSS. And he is a specialist in re-space theory, Banach space, Banach lattices, and ordered stuff, generally. He will be talking today about free Banach lattices. And by the way, he has been to visit us in South Africa a couple of times. This is the 5th time he's been to visit in South Africa, and he is a most welcome guest. Youssuf.
Thank you very much. Thank you, Bruce. Thank you for this opportunity. In fact, my talk is about free Banach lattices, but especially in some, I will focus on some property called strong Nakano property. In fact, this topic is new for me also. So it's a recent area, so I can, in fact, here there is a, we can work on a Banach space, there is a norm, and this is the recent, unless the topic is general, but for free Banach lattice. So Banach lattice, there is an old topic, and there is many books and papers about it. But for free Banach lattices, the first paper in this direction is in 2015. So it's a paper by Debacter and Wixty. It's a very interesting and fundamental paper subject. So people wishing to work on this area should start by these two papers. The first in 2015, and the second is by Avilés, Rodriguez, and Lattices, 3 years after the first paper. And then the theory has been expanded very quickly. Just I mentioned here, there is a lot of papers after the paper of Lattices. I mentioned just one very important one. It's a memoir in the European journal. It's almost a book. So this third paper. And there is about, I didn't count, I think that about 30, 40 papers on the subject. But you see that the first one is in 15 and the second in 18. The first one contains a series of open questions. I think that it's about 20 questions. They are interesting and exciting, and gave an opportunity to publish in a very high journal. Okay, I can start by giving some basic thing. Just I am new in the area. I want to work in this area. There is a lot of open questions, a lot of authors interested in the subject. So, what's a Banach lattice? So, a Banach lattice, I start by giving some examples. So, our spaces, our usual spaces are in fact Banach lattices. LP spaces, the spaces of sequential, and space of continuous function on some compact outdoor space, or if you take a general topologic space, you can work on the bounded continuous function. So a Banach lattice is in fact it's okay. A Banach lattice is a space which contains algebraic structure and order structure and a norm, and all these structure fit together nicely. More precisely, I can give the definition. Yeah. Okay. So it's a Banach space. And in the same time, it's a lattice. So it's equipped with an order such that the infimum and the supremum exist for if you take two elements. Okay, there is a problem. So it takes a time, but after that, okay. This is the definition.
So you need to aim it at that machine.
At the first, it didn't reply, but after that, okay, I have to wait a little. Okay, the order is compatible with the algebraic structure and the norm. So the norm respects the order in the last condition. So you can think of the usual space. They are Banach lattices. Okay, people can be interested in yeah. Yeah. Banach lattices. You see, it doesn't reply.
Yeah,
Now. Okay, you can consider maps between.
I was wanted to ask a question. Yes, that's just moved.
So maps between Banach space are linear and continuous or bounded, and maps between Banach lattices, we want these maps to respect the order. So we are interested in lattice homomorphism, are linear and respect the order, respect the supremum, finite supremum, and infimum. Okay. Okay, this is the next. In fact, there is a lot of literature about Banach lattice. I will focus on, I will just give the series of properties that are linking order and norm. There is the monotone completeness, Fato property, weak Fato property, Nakano property, strong Nakano property, etc. So I will start by giving some basic things about monotonically completeness. So the space is all of these property deals with a upward directed set or an increasing positive net that is either order bounded or norm bounded. And we want some property linking the norm and the order. So for this property, if we take an increasing net, which is norm bounded, then the supremum exists. So you see that here we assume that the net is increasing, so this is an order property. And we add a norm property that is norm bounded. Then the supremum exists. Okay. Sometimes it's fast, sometimes no. I am here. Okay, some examples. So if you take a Banach lattice, or even not necessarily Banach, you can take X as a normal Dirichlet space. So you don't need the completeness for X because here we are interested in the dual. So the dual of every normal Dirichlet space has this property. The second dual is the dual that consisting of order continuous maps. So order continuous means that if the net converge in order to X, then it converge. Then the image converge. So the first is continuous with respect to the norm. The second continuous with respect to the order. And the third is continuous with respect to the order, but for sequences. because for normal, if you work with norm, so you work with sequences or nets, it's the same. The continuity is the same. But for order, there is two different notions. All these spaces are monotonically complete. So LP spaces are monotonically complete. Even L1, the other LP spaces are duals. And monotonically completeness implies order completeness or Dedekind completeness. So Dedekind completeness is a property that if you have a set which has an upper bound, then the supremum exists, like in R. Okay, another important property, the Fato property. Also, Fato property here, we start with an increasing positive net, like the previous property. But here we assume that this net has a supremum. And under this condition, we have this equality. So if the net is increasing, then the norm also is increasing to the norm of the supremum. Some example can take the previous ones. And here, there is a result that can give you more example. Regular sublattice inherit the Fato property. What does it mean? Sublattice is in fact vector sublattice. So take a closed vector sublattice. So we start by a Banach lattice, and we take a closed vector space, which is also a sublattice. So it preserves the order structure and the algebraic structure, and it's regular. What does it mean regular? Regular means that if you have a net in the small space, which has a supremum in the small space, then the supremum is the same if you work on the whole space. This is what does mean regular. Okay. Okay. Nekalo property. Nekalo property also we start with an increasing net positive, and the net is order bound. Then, if you compute the supremum of the norm of X alpha is equal to the infimum of the norm of B when B is runs over all upper bounds of the net. We know from the beginning that the net has an upper bound. Okay, so Nekalo property can be connected to Fato property like this. So the space has a Nekalo property only if it's Dedekind completion. So what's the Dedekind completion of this space in general? It's the smallest one. You can give a definition. Roughly speaking, it's the smallest one that contains X and it's Dedekind complete. It conserves some universal property, and we can equip this Dedekind completion of X by a norm that extends the norm on X. Because in Dedekind complete space, every upper bound net has a supreme. So you see that in Nekalo property, we didn't assume that the net has a supreme. But in Fato property, we assume that the supreme exists. So if we work in a Dedekind complete space, we can link these properties. In fact, so if the space itself is Dedekind complete, then these two properties are equivalent. And I want to mention that all these property comes from usual space, like integral space. So the most important theorem in integration are the dominated convergence and the monotone convergence when we deal with increasing sequences. But here, there is a difference between sequences and general nets. Nets are considered a generalization of sequences. When the index set is more general than the set of natural number. This example has been is due to exceed, so it shows that we can have the photo property but not the Nakano property. In the photo property, we assume that the supreme is. So, okay. Here there is a property which is stronger than the Nakano property. So the Nakano property said that the supremum of the norm is equal to the infimum of the norm if you take all the upper bounds. So, okay, this is definition. So you see here that if you compare this definition with the previous one, here we assume that this supremum is attained in some upper bound P. Okay, so we can speak now about lambda strong Nakano property. What does mean lambda? So in the inequality, we assume that B is less or equal than lambda multiplied by the supremum. And we can speak about lambda plus Nakano property. So we assume that the strong Nakano property is true for all lambda prime more strictly greater than lambda. So all say K spaces are have the strong Nakano property. KB spaces, or the KP spaces, I got the definition. So you can use. So there is a lot of definition linking the norm and the order. So there is what we call order continuous Banach lattice. Order continuous means that the order is continuous. So if X alpha converge to X in order, then X alpha converge to X in order. So the norm is continuous with respect to the order, the identity. And for example, all LP spaces are order continuous. So reflexive spaces are order continuous. And the KB spaces is a special class of order continuous spaces. So in fact, KB spaces can to reach Banach spaces lies order continuous. And for KB spaces also the definition links the order to the norm. And if we add the strong Nakano property, we get an equivalence between KB spaces and order continuously strong Nakano property. If X is separable, then we can deal with the sequence. So I say that all these properties are stated for nets. So we can have the same property for, there is two different properties. For nets, it's general property, and for sequence. So, and they are not equivalent. So in fact, for separable Banach lattice, we are concerned here on Banach lattice. The strong Nakano property is equivalent, lambda strong Nakano property is equivalent to the lambda strong sequentially sigma Nakano property means that we deal only with sequences. And we can find some example when so I can give you the example here that you take X, it doesn't appear. You take X, all elements in L infinity of R with countable sequence. This is a Banach lattice with the supreme norm, which has the strong sigma Nakano property, but fails the Nakano property. And you see that here, we assume that the supremum is countable. So if we deal with sequences, it's a union of countable systems. Okay. I can give you some results connecting these. Okay. So if you assume that the space is monotonically complete, then all these properties are equivalent. I recall that monotonically completeness implies order completeness. And all this stuff we didn't use the free Banach class. The title is a free Banach class. So these are general properties that link order to norm in general Banach lattice. Okay. The talk is based on a joint work with Asma Berjab and Pedro Tradeset, and the paper is called Strong Nakano Property. So for this reason, I focus on this property. And usually we are interested in studying if the property is conserved by taking subspace or superspace. So here there is a result. If we work in Dedekind complete Banach lattice, then we have this equivalent. Here the space of regular operator, I recall that regular operator means that it's a difference between two positive operators. And positive operator are operators that send positive element to keeps positivity. And if you have a sublattice which is ordered dense and has the strong Nakano property, then this whole space has the strong Nakano property. And just here a remark that Pato property is inherited by taking regular sublattice, but for the strong Nakano property, it's not the case. Okay. So it's not the case even if the sublattice is regular, so it respects the problem. The strong Nakano property is not conserved. So we need to take more restrictive conditioning. So here, if you assume that Y is a sublattice, but is a completed sublattice, so you can write we can write as a direct sum X is Y plus Z. So we have some projection from X to Y, and we assume that this projection is regular. So it is a difference between two positive regular. Then if the space has the strong Nakano property, then Y has the strong Nakano. And there is some why we are interested in this strong Nakano property because there is some interesting open questions in the first paper that I mentioned by De Vector and Wicksteed dealing with these problems. Okay. Here there is a property that projection band inherit the strong Meccano property because it satisfies the previous condition. Okay, if you take a projective Banach lattice, what does mean projective Banach? I think that I mentioned the definition here. Yeah. So projective Banach lattice means that if you have epsilon fixed and a Banach lattice X, any Banach lattice, and any closed idea J, and you consider a map from Z to the quotient, then this map can, continues, can factors through the quotient. So, and we have a control on the norm. So the norm of T hat is less or equal than 1 plus epsilon, the norm of T. So projective Banach lattice has the 1 plus strong Meccano property. What does it mean 1 plus? But we have the lambda strong Meccano property for every lambda strictly more than 1. And here in the second paper, I mentioned that I said to you that there is 2 fundamental papers on the area of Banach lattice. Now, in the second one, there is an answer to a question by De Vector and Wicksteed about this answer a question. So here the free Banach lattice of L1 of A. I didn't already give you the definition of free Banach lattice, which is the main topic of this talk. Okay, what is the free Banach lattice? So this is an important thing. It's somehow not easy to understand at the first glance. So I try to give you the whole idea about it. So to have a free Banach lattice, it's a free Banach lattice generated by something. What is this something? It can be a set. So we use this notation, the free Banach lattice generated by A. Here A is a set. It can be a Banach space, and the notation is changed. So it's and it can be a lattice. So we have another notation. L is a lattice. So E is Banach space, and L is just a lattice. 3 means that if you start with a set, there is no connection between elements of the set. And for the second one, for me, the second one is the most important. So we start with a Banach space E, and we construct a big space which contains E, and which is a Banach lattice. So it respects the Banach space structure, and it adds the lattice structure. So you can think like if you start with a set A, and we construct a vector space, and take a finite set, and you construct the vector space. This is the free vector space for which the elements of A consist of base. So all elements. All finite. Okay. It is a Banach lattice together with a linear isometric, linear embedding. So we have space E. There is a map from E to the free Banach lattice, which is an isometry. So we can see E here. We have a copy of E in this big space. And it satisfies, here I use the letter W for the free Banach lattice, but the usual notation is this one. Free Banach lattice generated by E. And we have a universal property. Maybe it's important to. So this space satisfies the universal property. So you have the space E. E is inside the big space FBL of E. So you have E, FBL, E. This is the map delta. So if you take any Banach lattice X, X is a Banach lattice, and you take any linear, bounded linear map, then you can find T hat here, making the diagram commuting. So you have T equal T equal T hat. Another condition that the norm of T, because we assume here that T is linear and bounded, the norm of T is equal to here there is a constriction due to Aviles, Rodriguez, and Traverset in the second paper that I mentioned. So we start with the space E. For every X in E, we define a map delta X from E star to R in the map. And after we will identify delta X with X. We will see X as an element of the free Banach lattice. And we consider the space H1 of E consisting of all positive homogeneous map. So here, maps are defined on E star, from E star to R, but we don't assume that these maps are additive. We assume only that they are positively homogeneous. So H1 of E contains, but there is another condition on the norm. And for the norm, it's a little complicated, the definition of the norm. You see here that the norm of F is this supremum, is this supremum. So you take all this sum under this condition. So we assume that this sum is less or equal than 1 for every X in the ball of E. And under this norm, okay, this can seem to be some strange norm, but it comes from the idea of the first paper of Debacker and Wixty, when they consider a set of Banach lattices generated by a set, not by a Banach space. So you can forget about the norm for the beginning. We have just a space which contains E equipped with some norm. This is like expression. And in this space, this is not the free Banach lattice. It is a big space. In this space, we consider the closure, the smallest closed sublattice generated by delta x. We can think of delta x as x. This is the free Banach lattice generated by E. And the notation is this one. And for the norm, in fact, we use this one. Okay. Okay, but we can have an easy point of view. We can think of the free Banach lattice of E as a subspace, as a space which contains E, and such that this is a better and easy thing to consider, at least in the beginning. So we have a space E. And what's the Banach lattice generated by E? It's superspace such that I will consider this way. I will assume that E is contained here, such that if you take any map from E to X, what is X? X is any Banach lattice. Then this map can be extended to the whole space. Here there is no lattice structure, but here there is a Banach structure and a lattice structure. And this map can be extended to the whole space, but the extension is a lattice homomorphism, and it conserves the norm. So we have okay, here you see the not here. You see that you have you have this space, and you have an explicit formula of the norm. In a paper for a short paper to Vladimir Drutsky, he takes this point of view, adopts this point of view, and he consider all norm or all lattice norm that extend the norm from E to some superspace without giving an explicit formula for the norm. If you consider a maximal lattice norm, then he can construct this space. So the norm is maximal between all lattice norms that extend the norm from E to this space. And he showed that there exists some norm. So it just deals with the properties, not the explicit formula of the norm. And it can be easier because you can think of like you have the Banach theorem. If you have a subspace and you have a linear map from E to R, just a number, then you can extend with the same norm. But here the extension is unit. So, and we can show that Banach lattices, three Banach lattices exist, and it's unit. So for the existence you have this one, and for the unicity you use the universal property. Okay. Why people are interested in this complicated space? There is some motivation, and day after day, papers and results prove that these spaces are very important. First, we have a new class of spaces. They are not known before. So even if you consider E a space with one dimension, then the free has two dimensions. And if you move to two dimensions, then the free Banach lattice of E has infinite dimension. It's closed. And these spaces are new and not known for people working on function analysis and relative theory. For this reason, these spaces allow authors to answer some open questions. I just mentioned this question due to this step. The question, I explained the question, is every lattice weakly compact generated by a lattice is weakly compact generated? So if you have a Banach lattice X, and if you can find a compact space. If you can find a compact subset such that the smallest closed subspace generated by K is equal to X, we say that X is compactly generated. But here, weakly means that we use the weak topology. Okay, so this is the meaning of weakly compactly generated subspace. Now there is another, this weakly compact. What does mean lattice weakly compact generated? So we take not the vector subspace, we take the sublattice generated by K. I will use this notation, but so here algebraic and lattice operation are allowed, and this should be bigger than this because we use linear combination and lattice operations. So if we have this condition, we say that X is lattice weakly compact. And the question of this term is the following. Okay, so after studying 3 Banach lattices and some example of them, Avilés, Rodriguez, and Radecet answers this question. I just mentioned this one, but you can see the bibliography. There is many important open questions that people become able to answer using this new efficient tool. And for this reason, I become interested to this area, but I am starting. We are interested in some special point concerning strong Nakano property that I mentioned. And if you consider the free Banach lattice generated by E, if you assume that this space has the lambda strong Nakano property, then E cannot contain a subspace isomorphic to C0. This is one of our new results. Also, we were able to improve a result obtained by Avilés, Rodriguez, and Radecet, that the results states that the free Banach lattice generated by L1 fails the Fato property. Hence, it fails also the strong Nakano property. Just I want to mention something, even if I have no time to speak about all different aspects. I'm just interested in the free Banach lattice generated by a Banach space. But this is the second items. The first was the three Banach lattices generated by a set. And in fact, this is a generalization of this one. So because this one is equal to the three Banach lattices generated by L1 of A. So the first paper of debugger, we studied this topic. And the second studied this one. And this one is a generalization of it. And even the first paper contains a lot of open questions that some of them are not yet solved. So you see here that okay, this is our result. What's the difference here? That if the free Banach lattice of A has a lambda Fato property for some lambda, that E does not contain a closed subspace isomorphic to L1. And the previous result is a closed sublattice. And there is only few spaces that if you can embed the spaces in a Banach lattice as a closed subspace, then you can embed them as a closed sublattice. We are also interested in the free Banach lattice generated by a finite dimensional space. Even if you deal with finite dimensional spaces, things are not easy. And it was proved that the free Banach lattice generated by a finite dimensional space has the lambda strong Nakano property. But this lambda depends on the dimension of the space. And what we have shown that, in fact, we can, the first is our new result, that we can found a universal constant that does not depend on the space. And now we are interested, we don't know, but it is possible, it's still open if it is possible to make lambda equal to 1. The proof is technical and
you probably have about 0 minutes or 2 minutes.
okay. So I will, I think that any talk should contain a proof. And for this reason, there is a proof. It's based on a series of lemma and the technical result to Zarek. I think that the talk is somehow technical, and we have a lot of properties. And even if we focus on one of them, it's not so easy because the norm, the space itself are a little complicated, and we use a lot of things. Just at the end, I want to mention that there is we can consider free Banach lattice the notation. I can't make a correct notation in the title. This is the notation. And there is some modification in the norm, so and the property. I didn't give the definition, but there is a generalization of the free Banach lattice. So the free Banach lattice generated by E becomes, in fact, the free Banach lattice generated. This one is, in fact, the free Banach lattice 1. So we can consider this for P between 1 and infinity. For P equal infinity, things are different. And after proving some results in the free Banach lattice generated by E, people are interested in their generalization for free Banach lattice P. This area is new. It contains a little of questions. You should be familiar with the notation and norms, etc. So to work correctly. It's nice to work to manage some a mixing of properties coming from order and function analysis and topology and put them together. It's nice to work.
You have an explosion or a soup.
So I want to thank you. There is any question?
Are there questions from the audience? I have a question. You didn't talk about the last one, the lattice version, where you generate your free Banach lattice from just the lattice.
Yeah, but because there is a few, it's the last step, in fact, in the publication.
Okay, it's in your publication.
Yeah, it's a new thing. Even in the first, just I mentioned that even actually that's generated by Banach space is a generalization of the set, but I didn't speak about this. They are different things, but they all can be linked. The more important, it's this one.
Okay.
And, this one, there is a lot of results.
Is it available on Archive?
Yeah.